Hi, we're continuing the discussion for floating points, and just to make sure that we understood the order of this lecture. What we did in the previous examples, we looked at. Whoops, this is not writing appropriately. We looked at the previous examples about right how to convert from decimal to floating point formats, and then we're going to pay attention to the case when you have the exponent is zero. So we say this is where we will look at the fraction here. If the fraction is zero, then this is a true zero. Okay, so this is basically the value of a zero. And in if the fraction is non-zero, then we talk about a denormalized number. What's a denormalized number? So here is the line number, the number line, and we have here the zero value, and we have here the smallest number. Between these two, all these numbers are referred to as denormalized numbers. And those denormalized numbers, basically they are produced during addition, multiplication, division, math operations. And when we get a number which is denormalized, and basically this is not um, uh, cannot be represented in the format, but it gives you an indication that this number had fallen in this range, which is the denormalized, and typically it causes what we call underflow. Okay, so there is an overflow and there is underflow. And underflow happens for floating points when you have the result as a denormalized number. Okay, so this is a special case here, and we look again into when the exponent it has a value of a maximum value. Then again we examine the fraction. If the fraction is zero, then we have a value of plus and minus infinity. If the fraction is non-zero, then this is not a number and it is not a valid number according to the IEEE format or standard for the floating point. And obviously, you can see from this table here that we have a problem with the IEEE floating point formats, which many people have in the research community have raised as problematic. For instance, you have plus and minus zero. This denormalized is wasted. The not a number is a wasted range of codes. So a lot of people now proposing alternative system for the floating point, much like the posit and its cousins. Okay, so now let's talk about a floating point addition and multiplication. If we are multiplying, if we are adding two floating point numbers, then we have to go through steps. Suppose we are adding these two numbers, this number plus this negative number, and basically this is in the decimal what we are doing. The very first step, and notice that this is going through steps, and really the main idea of the next few slides is to register this fact that floating point numbers uh, uh, unfortunately comes with a heavy baggage of complex operations when we do additions and multiplications and divisions, etc. And therefore, the message here for you as a computer engineering student, and that this is what differentiates you from a person who is purely software, is that you do understand the load and the heavy execution that comes with the floating points. So this should reflect to what? Well, this should reflect to you as a programmer when you program code is to avoid floating points as much as you can. Well, of course, if you need them, use them. But to use them, I've seen programmers that they just pepper their code with floating and points, floating point numbers and doubles just sparingly. They don't like integers, they just throw. Well, for an assignment, a program for one of your programming courses, that's fine. But if you are not writing an app, that is not fine, because it will take up lots of memory, and it will be extensive execution, require extensive execution to execute these math operations behind or associated with the floating point. So this is what is involved in the add. Remember, adding two integers, just an adder. Here it is not just an adder. We go through the following steps. The very first step is that we align the binary points. And basically in here you see that these two numbers, we have two different exponents, and obviously we just cannot add the significance here because they are associated with two different exponents. And what we do, we align them, meaning we make the two numbers have same exponent to the larger. Which is the larger, -1 or -2? No, -1 is the larger, so we make the two numbers -1. So this one will drop as is, but this one we're going to have to move and shift the decimal point and then make this a -1. Now, once we align the binary points, then we add the significance, which is these numbers here. Okay, we add them and we get the result. Now, step 3, we have to normalize. Of course, whenever you do add and multiply, you will end up with the non-normalized, and we know the normalized is 1 dot something. Okay, so now this is not 1 dot something. We need to normalize, and then which means we have to make it 1 point da, 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 times we change the exponent. So we normalize this, and this becomes the number. Now, sometimes we need to round. If there is a 1 or a 0 here at the end, we need to do the appropriate rounding, and sometimes rounding trigger renormalization. So these are the very first steps of addition. Align the binary points, add significance, normalize, and of course we need to check for overflow and underflow, and then round and renormalize. And the hardware associated with this is for the floating point adder is as you can see. This is the very first number, the number 1, and the floating point number 2. And notice the very first thing we do, we compare the exponent. So because we need to know which is the larger one to keep. And then what we do, we shift those fractions. We shift this fraction or this fraction based on the larger of the two exponents, and then we add the significance. And then once we add the significance, we have to check if we have the result is normalized. If it is not normalized, we have to normalize it by doing shift left and right, so that we have 1 point xxxx as a result. And then we do the rounding hardware, and finally we express the answer in the IEEE format: sign, exponent, and fraction. Okay, and you can see the associated steps in terms of the previous example with the hardware here, so you can follow up with what's being done in the hardware. Here's what I want to pay attention to. Look how many LUs we have. Look how many shifters we have. Look how this is expensive hardware. Again, this is to register the fact: do not use floating and double unless you have to. And as I said, I have seen programmers, and I'm one of them, where we just use the doubles and floating points just casually, and not knowing back then the associated cost in the hardware for these numbers. Okay, so be careful. Now, so in terms of multiplication, again, we go through steps, and here's an example. Okay, let's go to a binary example. Okay, so we are multiplying this number by this number. Okay, the very first thing what we do is we add the exponent, and obviously here the exponent is this and this, so we add them, because when you multiply, you add the exponents. Now, if you are doing the biased values, make sure that the bias, right, if you add, then you will have double of the bias, so you have to get rid of one of extra bias. Okay, if you are having the values with the bias, make sure you subtract one bias, because you have double bias here. Now, we then multiply the significance, the numbers. We normalize and check for overflow and underflow. And okay, and after normalization, as an addition, we round and normalize if necessary. And finally, we determine the sign of this multiplication. Obviously, the sign is the exclusive OR of the two signs, meaning if you are multiplying positive, positive, negative, negative, the answer will be positive, and negative, positive, positive multiplied by negative, the answer will be negative. Okay, and of course the associated hardware with the multiplier and the instruction, the associated instructions and MIPS, I'll leave those for you as reading material for you to go over and study it yourself. Now finally we have this example of an ALU where this ALU is simple ALU that we can see that we have single bit A, single bit B, goes through a multiplexer here which has a control signal which allows us to select between A or A prime, and another control signal here which allows us to choose between B and B prime, and there is we produce or we AND the operands, whatever they are, we OR them or we go through an adder, and the carry in is an input here, and the carry out is an output, and the result, right, we can choose as an output of an AND gate, an OR gate, and the adder. And so, for example, if I want to say I want the result to equal A and B, so in this case, I need to select A, all right, and I need to select B, all right. So this should be a value of a 0, and this would be a value of a 0. Now I have A and B, right? And then here I have A and B, A or B, and A added with B plus the carry in, okay, the carry in. So obviously the answer here is I need A and B, so this operation should be set to 0, and at the output I have A and B, okay? What if I need, for example, let's say, for example, I need A prime or B prime. Okay, so here instead of selecting in these maxes A or B, I'll set it to 1, and that's where I'll get A prime, and I'll set this one to 1 as well, I'll get B prime, and then here A prime, B prime, and the operation should be set to 1 so that I select this one to the result. So you can see the simple ALU allows me to do a simple logic operation, simple math operation, and for a single bit. Obviously, other ALU design are much more complex, but the idea is that you have to be able to prepare the data or condition it the way you want in terms of inversion, and in higher order operation we can think of twos, complements, and what have you, and then perform in parallel certain things where you just can select your final answer. This is based on your opcode or based on the code in the that you want to select. Okay. With this, I think we can say we conclude this chapter. Thank you very much, and we'll check with you on next lecture with the next chapter. Bye bye.